All right, let's get started. This is your signature. So before we begin, I think there are a couple of two announcements. First is that there will be a makeup lecture for the one that we missed on Friday, and that's going to be tomorrow at the same time. But in the auditorium 1030, I don't know where it is, but it's not in the same time. So this is income. Let's see. And at the same time, and for you that you are coming in person, that's I have updated this schedule also on the course website, where I will also upload the recordings of the lecture. So that was the second announcement. Hopefully later today, because some of you, especially from Zoom, yeah, sure. So, especially from Zoom, we're asking have the lectures uploaded somewhere. So I'll do that today. So that is there is 101 and 2. Actually, there was also something else which was coming from another question that you made, which is about this Latin American Congress on Industrial and Applied Mathematics. That's going to take place here at the FGV from starting in January, on January 3rd. So the Monday after this was finished. And there are going to be a lot of topics on it and applied math. But we are also organizing a special session on the mathematical foundations of the world. And here there are going to be 7 talks from speakers around the world talking about ways we can, or mathematical tools that we can use to control work. Some of them are going to be some other aspects or some other ways of using optimization for robots. Others are going to talk about different topics, right? Or different mathematical tools. So I think for students, it's the registration and attendance is very convenient, and the registration fee is very low, and you get access to a bridge problem. There are we are just in this special session. We are just here. Here on Monday afternoon and on Thursday afternoon. Then there is a lot of other sessions going on and plenaries, panel discussions and conferences. So that's pretty exciting. If you are around next week, that's probably a nice lecture for that. That's that. This. All right. So I think, yeah. Stop sharing and do this. All right, so the lecture notes are updated on the website with. Oh, yes,
Can we try to fix the feedback now?
Oh.
I think use one of the computers.
One of these computers.
Yes,
It's fine.
so
I don't need this, right? Is it better now? Let's. Should be, right? Let's see the opposite. Okay. This, by the way, is another instance of it, right? So in this case, there was this computer. There was a hitting sound, right? This sound, this here. And there was a microphone that is feedbacking this sound. Why does this result in this annoying behavior? Right? It's because I'm talking in this microphone, which is somehow the desired input. There's the undesired input, which comes from here, which is sound. So let's say my voice. Right? So the difference with the feedback loop that we saw in the first lecture is that here the reference from the reference we subtract the feedback. Right? If we subtract the feedback, then we act on the error, which is getting smaller and smaller at each loop. Right? Whereas in here, we're acting on the sum. So this is going to get higher and higher, so larger and larger. It's going to explode eventually. Plus, there is also delay. Here. Right? So this also, let's say, contributes to this instability. There's the way to get things to work is the negative feedback. It's negative. Because of this sign, this negative sign. This is the positive feedback. I think positive feedback is a word that is used also in everyday life, right? So there is a positive feedback effect, which we try to use in a positive way, like is reinforcing some good behavior, right? I don't know, like working in an environment where everyone is excited to work is good for you get excited to work, right? But as in an environment where everyone is sad or hates working, it's not helping, right? So that's a good positive, right? Or the spreading of news, right? Hopefully that's a good thing because you get news to reach.
E o seu hashcode, tá? Esse hashcode vai ser utilizado para você fazer o SSL.
Who is speaking here? Make sure your mic is unmuted only if you need to say something relevant. But yeah, so that was parenthesis on this. All right, so let's see. Let's go over what we talked about last time and see if you have any questions. If you have any questions on that before we proceed today with the second class of robotic tasks that we will deal with, which are the invariants, right? Awesome. I guess last time there were a lot of information Okay, so it's probably good to have a short pickup. Now. This is last time, which is when we talk about stability like so stability like us, the picture is that we have a set triple S that is in the state space of the robot. In our case, the state space is the space where the state of the robot lives, is Rn. So S here. Here we are in Rn. S the subset line. And the stability like us consisting starting from the initial condition of the state that is x at time t0. We want the trajectory of the state try to approach the set s as time goes on, which is written as x of t converges to s. We said that we use this symbol to say that x of t is going to belong to s eventually, so as t goes to infinity. So that's an asymptotic property. As time goes to infinity, we want x to approach set s. And we said examples of these tasks are regulating the effective force of the manipulator. Desire. So driving a mobile robot. By desired location. And then we also mentioned a couple of others like trajectory tracking. Or we said orienting the end effector towards a desired point is still can be still considered as or modeled as a stability rate. End effector. The point of interest. And towards. So we only care about orientation. These were examples. And we said, okay, let's consider a model which is capable of representing both manipulators and mobile robots alike, so that we don't need to specify things for the two types of robot, but we can develop a theory which works for any kind of system that we can model this way. And we use the so-called non-affine. Affine robot dynamo, which are x dot equal to 0 x and 1. X. U is the control input. And is a vector in R M. Control input means that is the set of values, the selection of values that we need to supply, right? The set of quantities that we need to supply to our code. We saw examples of this, right? This can take the form of the kinematic and dynamic models that we saw in the first lecture. It's like, which are like that. Or we got this is kinematic of manipulator. This kinematic of mobile robot. And then we said also the dynamic model of manipulators can be expressed. In that case, we didn't see it, but last time. But I have that in the notes. Right? That is a little bit more complicated, and it also has this F0 term. F0, by the way, is sometimes called the prefix. Because as if you remember, we said that this appears only when there are, in the case of mechanical systems, dynamical effects like acceleration, acceleration, centrifugal forces. But basically is representing the effect of inertia, and that creates the drift. An example of the car that is controlled using acceleration. If we release the pedal from our car, then we're still going to move because of this thing. Because we still might have a non-zero velocity, even if we remove the acceleration, we set the acceleration to zero. Then as we brake with this u, we get to x dot is equal to zero. So in this case is this drift consists on the velocity of the joints. Here we have the inverse c times dot times g. But these are the centrifugal, gravity, gravitational effects. Right? Plus, the inverse. It doesn't matter the expression inside, but the idea is that this represents the inertia in T and the centrifugal forces at C. Whereas this is the F1 of X, which is the torque, the external torques that we give to showing torques. This is the dynamic of it. This is just an example. As we said, we are not going to deal with this model in context of this course just because it's just more calculations. But the formulation is basically the same. Right? So we're going to concentrate on kinematic components. For manipulators and applied problems, which like this. Then, once we figured out the dynamics of our system, the execution of the task, stability like task, becomes right. How execute activity like becomes big U in Rn such that x of t converges or goes towards s as t goes to t. And how does U control x? Through the dynamics. Right? So x moves hopefully towards s following the dynamics. 0. That's how U influences x. Now we said this is a difficult problem because we need to pick a vector U to influence the motion of a vector x. So in general, that's not easy. So we said let's simplify. So this is hard. It's hard. So we said let's simplify it to be a one-dimensional problem. One. And how do we do that? We choose, or we try to find anyway, define the control the output function at V, which takes the state from Rn and maps it to scalar value in Rn. In particular, this value is also positive because V is positive negative. Then they're equal to 0 for all x's. And V of x is equal to 0 if and only x. So that now the problem, thanks to this positive definiteness property of the function becomes just write the value of V to 0. That's it. So the picture here, the parallel picture is if as time advances, we start. So the value of p starts at p of x at p0. And then as p approaches s, p approaches 0. So for example, this is p of x at p1. This is x at p1. This is x at p2. This is p of x at p2. Eventually, as we get closer to p of x at value p3 becomes 0. Let's closer to 0. The dynamics with which this p goes to 0 can be found using chain, right? Because this moves in Rn, this moves in R, right? So B moves on a line, right, which is R. And the way it moves in this line can be found using chain rule. The B dot is the BDT is the BDX times X dot, where X dot is given by the controller line. So this way, we somehow explicitate the effect of U, the control input that moves X in the state space, on B. And as we did that, we also, in a way, can enforce constraints on this U, such that B goes to 0. So we said, how can we ensure that B goes to 0? Well, we just ensure that it stays below a function that converges to 0. And this line is the solution of B dot equal to minus alpha, where alpha is what we call the class A function. We can think of just multiplying B by a positive scalar. That's an example of class A. So if B dot stays below by satisfying this inequality, then we know that it's going to go to 0. These constraints become constraints here, where B dot is here, is this, becomes just a B x 0 x plus x and 1 x times U less than or equal to minus alpha of B. So as for each x, right, we plug in its value in these formulas, right? So we evaluate this, we evaluate this, we evaluate these three numbers, or three vector numbers, and we have a constraint on it. There might be multiple views that satisfy this inequality. So the one that we decided to pick is one that minimizes the norm of the vector U. So now the answer to the question, how to execute stability-like tasks, becomes take a U in Rn, such that there we wrote x of p goes to s. Here we write p of x of p goes to 0 as p goes to 2. Which is the same as such that p dot of that depends on p of x p dot depends on x and q. It's less than or equal to minus alpha. It's the same as this. So we said that meaning energy formulation is the solution to this optimization. But the cost is the square norm for Q. And the constraint is this. Object 2. The cost is quadratic. The constraint is affine. So quadratic integration variable. No matter how complicated these functions are, right? The dx times f0, dx times f1, alpha will be met. Doesn't matter how complicated they are. U shows up here as in an affine dependence. And this quadratic cost with affine constraint gives us a complex quadratic. And why is that good? Good. Because we can solve it using very simple and efficient algorithms. Very simple because we saw one of them, right? We basically found it by in the very beginning of the introduction of the optimization, which is the gradient descent. For the unconstrained, for the constraint is just a small variation there, but it's very similar, which returns us a local answer. But since it's a complex problem, it's also the unique global. So with a very simple algorithm, simple, efficient, and fast, that means fast, we can find the best of the best, right? Solution. Do you have any questions on this procedure? If it is all clear, then today's lecture is going to be straightforward because you're going to basically repeat it almost as is, right? With one difference. So in the stability like tasks, we would like the value of a function, right, to go to 0. In the invariance like task that we will define today, we would like this value of the function to be positive. We just keep it above positive function instead of restricting it to this region that goes to 0. And everything else is going to be 0. Right? So let's do it. One note. This is an annoying expression to write all times. D dx times f 0 of x. There's a shortcut, right? Which is this. Have you ever seen this before? That's used a lot in differential topology, differential geometry. It's known as the Lie derivative of D in the direction of MC. So that's the derivative of a function in the direction of the vector, which is kind of generalizing the directional derivative, right? That we have for multivariable in multivariable problem. This is known as the Lie derivative of D in the direction of F. So in our case, this is an L, right? This is an L that stands for V and the letter L. For our purposes, this is just a replacement of this expression. So super easy to compute because we are in Rn. So x is in Rn, u is in Rn, right? So all Euclidean. So that's the expression we use when everything is Euclidean. For general manifolds, right, that which are state and lead, that the expression of this becomes more complex. That means that if we express things using this expression, right, using this notation, we also generalize to cases where the state is in a non-trivial manifold like Euclidean space. So this constraint right here becomes just it's much shorter to write, right? The optimization problem that we solve, which is minimize Q sub into LF P of X plus LF1 P of X. Sorry. LF0 P of X plus LF1 P of X less than or equal to -1. All right, so let's talk about invariance line tasks. So we said stability line tasks consist in driving the state towards a desired set. Invariance line consists in keeping the state within a desired set. This is the set, again, in Rn, where the state has to remain confined. It starts at x of t0, the time t0. And as it evolves, this set right? We want it to never leave. The trajectory and so on. So more formally, this means that if x at t0 is in S, then we would like x of t remain in S. Which is the mark for this bed. Why is it called invariance like classes? Because this happens when S is forward invariant. Or invariant. Forward just means that we are only interested in future times, times after 0. But to say that S is invariant means that if the trajectory of the state originates within S, then it never leaves. Now the question again is, how do we ensure that if we are starting within S, we are never going to leave it? Same question that we asked before for driving towards a set, we can ask it now for remaining. How do we ensure that X stays within the set S? Difficult answer is we pick a U, or easy answer, but difficult to implement. Right? Pick a U such that X of T is S in T, and X dot is equal to follows the plot-line dynamics. X dot at 0 plus everyone. Again, this is not an easy problem, especially the dual problem before, but it's for the same reason it's not easy. So what do you think we can do? Right? Taking the or keeping in mind what we did for the stability levels.
I'm confused. Why do we need to do that?
Wait,
Like, you have the algorithm for reaching this region.
yes, yes.
Why don't we just use this algorithm? So if we cross the border, we
Cross the border. Oh, you mean cross the border? We go outside. Oh yeah, that's a good point. That's a very, very good point. Because that was the way in which this kind of invariance property wasn't sure until a few years ago. Right? Using the same kind of idea, as you move towards the, so if you are basically right on the boundary, this set, you would drive towards inside. You said if we are outside, we drive inside. This could be a problem, right? In applications, right? Because what kind of tasks actually can be modeled using this kind of approach? That would become clear. All tasks which are somehow related to safety, right? Because if you give your robot or some function, right, of the configuration of your robot within a set which is safe, then behavior of the robot is going to be safe. So let's talk about example applications here. But this could be for a manipulator, and here there is a human. The human is manipulated with one joint and 16 wings. Anyway, we would like to keep the robot away from, let's say, this region. Right? So the set S is this, and the complement of this box. Same thing for mobile robots. Now we have a mobile robot that moves in the environment, and then there are obstacles. These are mobile robots. And there are obstacles. There might be humans. There might be regions of the environment where we don't want our robot to go for any other reason, like maybe algorithms do not work, like the camera is not usable, but for any reason we might want some regions of the environment to be not to be visible. So the set S is everything else, right? So this workspace minus is obstacles. So in this case, S is kind of the free space. So where free is stand for obstacle free. Obstacle free space. But these are not the only examples. Right? One other example, which might not seem something related to safety, is we want to have a mobile robot that moves in the environment, does tasks. Then it has a battery, which limited capacity, and then there is a charging station. Here there is a battery. Which I will represent later. That's the battery of robot. Now, the set S be the set of energies which are above a minimum energy. So S in this case is kind of the energy of the robot such that it is greater than or equal to E minimum. So E in this case is part of the state of the robot, part of the X. Right? And so if we want X to be confined in this state, we are saying that we don't want the energy to drop below it. Right? So as the robot moves, we would like it to basically reach its charging station, while let's say this is the level of energy here, when its energy is depleted. As the energy gets closer and closer to the minimum, we want the robot to drive it. This is also a task that can be encoded as an invariance. So the thing that has to remain invariant, set that has to remain invariant, set of energies which is larger than the minimum. But formulation is the same, even in words, right? Safe set or invariant set, in this case, is the set where the energy is greater than a minimum threshold, maybe. Here, the invariant set, which we can call safe set, because it's a safety consideration, is the set of positions of the robot, such that the distance from the obstacle is somehow larger than a minimum distance, right? Larger than zero, right? Potentially. So we want to We want to be able to stay in the whole free space. Same thing here. Is a set of configurations such that no parts of the robot or the effect of the application is closer than a minimum distance objects. But even in English, they sound the same. So you can see why the formulation, the mathematical formulation. Now back to your question. You said, why can't we use the stability like tasks to achieve this? So in this case, you're saying, yeah, if we hit the human, just go back. Right? Here, if we hit the obstacles, just back up. Right? Here, if you discharge your energy, just what do you do? In this case, you're actually getting stuck, right? But if you discharge your energy between a minimum threshold, you might not be able to get to the transition time, right? So there are cases in which, sure, you can do that. Maybe it's not that, let's say, not a tragedy, then if you go out, they said. But there are cases in which, if you go out, then you cannot go back in. Right? So that's why we would like to find another way, right, of remaining in this. So ensure that we never leave it. And if we leave it, there are other questions to be asked. But for now, let's say we don't want to, we never want to leave. So what do? We pick a unit such that when x moves this way, it will always stay in S. Right, now back to my question. How can we simplify this? Right, so following the same procedure that we did before, we want to simplify B one dimension. So instead of controlling the n dimensions of x to stay within the set S, we'd like to control one value such that if this value is in a given region, then correspondingly x is going to stay in the set. So here's let's define a function h that maps from Rn to R. Again, we would like to transform the state into state of computing, whose zero super level set is S. Have you heard of level sets or super level sets? Really easy. You've seen the topographic maps, right, where you see the level curves of the height of the elevation and of the territory in the region. So if we are, let me take the example that I'm on the notes. I try to go on the that my way of drawing the neighborhood bootstrap. And you have level curves, which represent these three colors, which represent the levels of 50 meters above the sea level. Then you have 100 meters. Okay. Let's say 200 meters. Okay. And then you have 300 meters. Right? So I think this is the how this is called the model term. Right? Now the there's 200 meters. And this is 300. Now, the 200 meters of the 200 super level set of the elevation function in this region is this. Right? So this is this, in this case, 200, if we express it in meters, super level set of this function. 300 super level set will be this. The 0 super level set of the elevation function are all the regions of Miller, for example, that are above the sea level. Right? So almost what we look at the planet sphere, the map of the world. It's almost the 0 super level set, the elevation function of the. As the 0 super level set of a function h, which the mathematical expression in this picture is that the set S can be written as all the x's in Rn such that h of x is greater than or equal to 0. Right? So that's the same here. All the regions of Ultra where the elevation is above 200 meters. The level set, it's not super level set. The level set, the 0 level set of h. So h equal to 0. That's the 0 level set. Means that we are on the boundary of S. X is on the boundary of S. Which represents this sign symbol. So in this case, the 200 level set is this curve. Whereas H positive means that we are in the interior, X in the interior of the set S, denoted with this circle. And H negative means that we are outside in the complement. Oh, you can't see? Let me do it. So that's it. Okay. This is S. So on stick figures, on the boundary, they said H is equal to in this region. H is negative. This is the picture. Again, we reduced from n dimension to these n numbers, right? Such that we are in the n dimensional set S to one dimensional problem, which is U that H of X of V is greater than or equal to 0 for all of you. This is a number, a scalar. I think again of this example, right? Instead of trying to walk right on the mountains, then look at the region in which we want to stay. We just look at the elevation, and we have some measurement of the elevation. And as we walk, we see the elevation going up and down. But as it's going, let's say close to 100, right? Let's say we want to stay within these three regions. As it's going closer to 100, we need to figure out a way to move in such a way that this number doesn't move below 2. And how do we figure out how this number moves? Right? That is the dynamics of H. So how do we find the dynamics of H? How do we find H dot? You think? So H depends on X, right? So the elevation depends on our position. So how can we find out how the elevation changes based on our position? Yes, that shows up in the if you apply chain rule. This is the H, which by chain rule is the gradient of H times X. Exactly. So this means that if you're looking at the elevation and we know the gradient, we're saying, oh, here we're going down. We don't want to go below 200, then it means that we need to go the other way. So this tells us the direction. Same thing for the diagonal function. It's the same. That tells us the way to go to 0. Here, this tells us the way not to go below, in this case, below 0. So the HDX times vector, which is substituting the dynamics of H at 0x plus F1 over Q, which is now using shortcut notation. LF0 Hx, LF1 Hx times this is again short for the HDX times F0 over short for the HDX times F1. Very convenient. I count this way, but it's not intensive, just gradient times value this way. So now that we know how it moves, how do we keep it possible? X of t has to be in S, equivalently, H of X of t has to be positive. Must be in the set of real values greater than or equal to 0. That's the set version, set theoretic version. See. Right. Again, let's draw the, let's say, desired evolution of the function h over time. If at time t0 we start positive, what does it mean that we start positive at time zero? It means that we are inside the set. We would like this never to go below zero. So let's pick a positive function. It's a positive function. We can pick the exponential. And make sure that R h of x of t stays above this. This is h of x of t. Which means right, we travel here. Then our state would mapping travel from here here. Right, but still within the set. In fact, the location of this xt1, right, depends on the value of each xt1. Just like the elevation again. Like where are we? If the elevation is we started at 200, we started at 250, 150 meters, we go down to 130 meters. Then we have to be somewhere on the level curve of 230 meters. Huh? But inside the set of above 200 meters, right? Right there is yes, right? So we will start here and then we will go down a bit towards 200, but we never exit the 200 super limits. Now, just like we did for the control function, this vector is the solution of h dot equal to minus h and h at time 0. I just write it like that, but this means h of x at time 0 is equal to hc, the initial condition. Now to stay above, what do you think our h dot should be? Should be greater than or equal to, right? Minus h. So if we start at the same place and the rate at which we move is always larger than minus h, then we can never cross this black line. So we're always above. How do we write this? We know h dot then h dot greater than minus h can be written as L at 0 h of x plus L at 1 h of x times greater than or equal to h. That's right. So here I explicitly written the dependency of the age x. There is a, of course, there is always a dependence on time, right? So this is the age of x of t, a h x of t, u of t, blah blah blah. It's clear. I hope it's clear about this. So that now we went from a constraint on h to a constraint on u. This is a constraint on u from u. So that if we pick a u such that LF 0 h plus 1 h still 1 equal to times h, then h of x is 0 positive. If we start with positive value, it will remain positive. Right. So if h starts positive, it will remain positive. Or if x at p0 is in S, H positive means that either is here or on the boundary is in the set S, then x at P will remain in S for so now we have almost done, and we have a systematic way of choosing an H such that our state never leaves the desired state. Just like we did for the control function, or generally, we can define H of Rn, the class of functions, H from Rn to R, such that H is continuously different. And the set S is the set of axes in Rn, such that H is here. Is so-called control barrier abbreviated as EF if again there exists more generally a class A function alpha. So the roll axis in Rn, this can be restricted towards a smaller set, but if that holds, then still okay. Roll axis in Rn, there exists in U such that if we use the inf from relation last time for the cell, the inf of something was less than 0. Doesn't matter. This is actually LF0 of HX plus LF1 times 3 greater than or equal to minus alpha of H2. So this that exists a U such that could be written as the suit right over U of the set LF0 H plus LF1 H times U plus alpha H. Sorry. But this is it's more useful in practice. The soup might still not be in size. But what we are concerned, we need to be able to pick a U, give to the robot. Right? This has to exist. This has to exist. So now the last step is to pick this U. Right? Once we have this kind of function, or variable, then decide a way to pick or define a way to pick a U so that H is kept positive. U, then minus the energy. Again, why should we pick any other U? Right? Can choose what U, right? If we can choose at which speed we should walk on the mountain to stay above 100 meters, why should we pick anything that is larger than B? Right? Why should we spend more energy? Sure, if we're getting close to the 200 level curve, we can run at maximum speed backwards, but why? Let's take the minimum energy, which is the solution of a minimization. Minimize node of U, subject to the constraint that L at 0 H max plus L at 1 H max is greater than or equal to H alpha minus alpha. Same thing as before. This is what happened. Fine. Okay. So that this is a convex graphic mode. And as such, can be solved very efficiently. Again, using computational tools, numerical algorithms that are available in many programming languages, computationally oriented programming. Okay, so let's do an example. Do you have any question on this procedure? Which is very much the parallel line, right? To what we did for this stability line. That's a very powerful way, like, of dealing with this kind of complex properties like stability or invariance, like reducing it to basically one-dimensional problem, and then figuring out in the end a control input, which is always our goal, right? We find a control to keep the robot such that simpler conditions are satisfied. The example is similar setup to last time for stability. We have a robot modeled by the single integrator dynamics x dot 0 q. So last time we said let's make it go to 0. Right? The stability like task was direct to the orbit or to a point. I think it was to a desired location x bar. Now this time, the invariance like task will be so keep x at least distance t away from a point which we call the x of the obstacle, right? Position of the obstacle. So this could be interpreted as safety distance and obstacle location. Right? If x at least a distance t away from this. Let's say we are not two. Right, so x is a point in R2. The location of our obstacle is somewhere here, x O, and the distance e is this. Right? So we want what is the safe, the invariant that or safe is to complement this goal. This is the set S. This is the set S, which now we will express as the zero superlevel set of a function. That's step one, finding this function. Find h. Then S is the set of x's where h is positive. Negative. How do you do that? Not that hard, right? In this case, h of x can be defined as distance from the obstacle squared because we need to take the derivatives. So it's smooth this way. Minus the minimum distance, the safety distance. Let's see if that works, right? If x, the x bar, such that h of x bar is positive, then what do we have? We have the distance from the obstacle is greater than or equal to the safety distance. So the drag region. We are at least be away. Yes. If h is 0, then we are on the boundary of the obstacle. And because we are at the distance d from the obstacle, so we are on the boundary. If h is negative, then the distance from the obstacle is less than d. So we are in the complement of the set x, so inside the book. Step 2 step 2 is to compute this derivatives to evaluate the expression of the constraint on you. So we need to write LF0 h plus LF1 h times 0 greater than minus alpha h. Now, again, this is dh at 0. What is that? H dx. Given that there is the h, the expression of h is the very similar to the output. This is the value. So it's 2 times x minus x. And then we have f0. What is f0? Dynamics are this. This is the drift of the single individual. See, there's no b. Plus dh dx at 1 x times u. dh dx is the same. Times u. Sorry, times f1, which is the identity mean, times u. And then greater than or equal to, what do we choose as a class A function? Let's choose this. So alpha of s is equal to a times s raised to. Explicitly, this is a times x minus x2 squared. This is 0. Okay. Here is the simple state that we need. Inputs. Let's write down the optimization zero. Basically substitute these expressions in our quadratic problem. Minus u squared object and x minus x whole transpose u greater than minus a times what is the solution of this optimization problem? let's assume X is such that, so X is in S. Assume we start in S, right? X is in S, which means this one is positive. What is the globally optimal solution? What is the laziest way we can move to keep X positive? H positive. So the right, let's look at the constraint. Constraint says 2 times that vector times u has to be greater than minus a, which is positive, from the plus a times positive. So minus a times the parenthesis is negative. So what can we place in as a value of u be greater than something negative?
You start specific.
Yes, right?
Okay.
Does it make sense?
Oh, sense.
It makes sense. If you are inside the set, we can stop right away by setting u to 0. We just stop and don't move. Don't move anymore. If you are on the mountain, we are going towards the level set 200, and we can stop. We are walking, and just walking here. And actually, no, we're not walking. Here we're not walking. Actually, we are inside the set, right? And then we want to stay in this set. What do? We don't move. This is 0. Two things. This is not the case when we have drift. If we're on a bicycle with a given velocity, and we are driving down right mountain, and we don't want to cross the 200 level set, then we need to brake. So our U star is brake. Some deceleration, but it's not 0, right? Unless we're going out. But anyway, there is not a thing, it's not as triggered as this. This only happens when we have just the invariance constraint, and we don't have it. So it's, I mean, as easy as it can be, right? To keep this system safe or set S invariant. The problem arises when this picture here. When we also have a stability lines. Let's say we want to drive to X bar. Right? Go this way. Now we're moving, right? So for example, we are on the mountain and we're very thirsty, and at 180 meters there is someone that sells water. Right? We want to get there, so we want to go down. So we are walking because we want to go down towards 180 meters, but we want to stay within 200 meters. Right? So at some point we're going to get close to the boundary of 200 meter superlimit, and we need to stop. If you, right, it's decreasing more and more as we approach the boundary, and then at that point you will see it. But before, it depends also on stability line. So this is the idea. Of combining stability and invariance line. how do we combine the tasks? Since tasks, both the stability line and the variance line are expressed as constraints, the easiest thing we can do is just enforce two constraints. Huh? So minimize u norm of u squared subject to. Now we have the stability line that tells us go to x bar. Which is it should be this, and this is what we wrote yesterday. This is b dot. This is equal to b dot. This is equal to dx times f1. And this is our p. Sorry, this is minus. That's the big line. You want to drive towards x bar. And then there is the invariance. Today, yeah, sure. Here is also call it A1, A2. There are just choices plus A function. A1, A2 times x minus x4. Okay, now it's non-trivial and it's not necessarily stop, right? Or don't move the optimus. Let's say, let's look at this picture and try to move according to the U star. So we are here, and let's apply U star solution there. So what we would expect is that at the beginning, since we may go this way without hitting this obstacle, the U star is going to fail. It's going to be like. Then we move closer and closer. At some point, when we get super close to pumping, we have two competing constraints. One is saying go this way, one is saying go this other way. And you can see it from this. These terms here. They look exactly the same, right? So one is from the derivative spatially pointing from it's pointing from x bar to x. Where gradient we are moving towards the goal points that way. So to decrease this function to 0, we need to go that way towards the goal. This one is a gradient that is pointing again towards us away from the obstacle. Now, though, we are interested in not decreasing this function below 0. So we need to go this way. Right? So these two constraints are saying go towards the obstacle, go towards the goal, go away from the obstacle. Which in this particular case is go in two opposite directions. So this is a problem. This problem is known as infeasibility. in is it because of competing constraints. Constraints are not independent. Include this lecture, we are going to see a general way of solving this problem. The next time we're going to see the implementation. We're going to see the implementation of such combination of invariance and stability vectors. The solution is the following. Now let's write in general V minus the norm of U squared subject to what do we have? We have LF0V plus LF1 V times U less than or equal to minus V. Yes. For the stability. And LF0 H of X plus LF1 H of X. Greater than or equal to. Sure, we can have general alpha 1 or B alpha 2. Right? What we can do is to relax this stability line task. And this is done using a relaxation variable, as it is called. Delta is a relaxation or slack variable which says you wanted this V dot, this is V dot, right? To be less than or equal to minus alpha 1 of V. Relax it to be less than or equal to minus alpha V plus a delta, plus a slack. Now this delta is an optimization variable, right? So we need to compute the value delta. It's not that we set the value delta. That's going to be something optimal, right? Found by this. Which of course, this is in a real value, and just a scalar that adds to this scalar value. And of course, we want this relaxation variable slack right to be as small as possible, right? Because we want to do this stability like that. But in case these are conflicting, let's relax the stability. But it's there. But then let's try to minimize this one. And here, kappa here just a. It's just as a scalar constant, right? To somehow sum the norm of U and this delta. To give more importance to delta rather than U or the other way around. Now the resulting behavior is that when we can execute both tasks at the beginning, for example, we're going towards the obstacle, we are far away from the obstacle. And delta can be 0. We can execute both tasks as we design. But then as we are getting closer and closer, this delta has to increase and relax the fact that you need to move towards this direction. Moreover, I think, yeah, I'll add to the collab also a plot to show how delta and P and H change, right, in time as we are doing. But the net result of what I said is that this is somehow equivalent to prioritizing the stability like task, sorry, the invariance task. Over the stability like task. Just as I said, as you're moving towards the obstacle, you're getting close to the obstacle, the priority is on the invariance. You don't want to hit the obstacle. Matter what you're telling me. And I'm not going to go into the obstacle, and I'm relaxing. Therefore, I'm relaxing. Trading off the execution of the stability line for the execution.
The first equation is operating the axis that moves towards the left.
This one.
Yes.
Yeah, this is encoding the go to goal. Like this is this the green.
And the second one is the axis of the position to the x0, but in the opposite way.
Yeah, so this one is this.
But if the program is in the same axis,
Yes, that's in direction. Yeah.
same direction, not like the axis, but it's really the same.
Yeah.
Then the problem can be solved even with the extra.
Without you mean without.
Yeah, without. No.
No.
Even with the variable, because they operate in the same directions. So we can solve either way.
You can solve it because what you're gonna do with this delta is the following. You has to be go towards the goal because of the stability line. So it has to be some value. In particular, has to be less than or equal to this. Or this has to be less than or equal to this. By increasing this value, you are basically including the control input that stops at the obstacle, right? In this feasible set. That's why this is called infeasibility. Because without this slab, the feasible set, so the set of views which satisfy both those things, is empty. Whereas by adding this slab, the physical set in a way enlarges, it grows. So as you're saying, oh, I want to go toward this x dot, x5, as you're increasing delta, you're saying, okay, it's okay if I just slow down and don't go to the front.
So if my system is symmetrical, the computer can get away.
Oh, okay. Now I see. If you're starting, and answer what you would like to say that if you're starting perfectly aligned, then the only way you can solve this problem is to stop at the bound as you're going precisely on bound. Alright, so you're converging to this one. If there is anything like any small number, a small component in the orthogonal direction, if it is on this way, then you're gonna go around the obstacle. If it is on the other way, then you're going to. I can show you some simulations, but you're right. On a computer program and simulation, you can get this kind of behaviors which, in the end, you are not going to execute your stability line because you're going to get stuck behind the obstacle, right? But as soon as you perturb it off just a little bit, you're going to move over.
So it is a problem.
In practice, it's not a problem, right? Because there is no such a exact alignment, right? Because the X, for example, when you plug in for real robots, that comes from the measurements of the joint angles or the position of the robot and position of the obstacles and so on. But this is never going to be precisely aligned. Right? But that's a great point. Like deadlocks, these are known as deadlocks, because you might stop even if your goal is to proceed, right? You keep going. So if you can imagine if you have a lot of robots that run this and don't want to each other, then you might get stuck. Like they all gonna stop and say, okay, this is the best thing we do not to hit each other. Right? Or we cannot achieve our goal. In practice, I mean, there are subtleties, right, that could make this kind of deadlocks arise, even if you're not exactly aligned, but you can converge to these points. But this is like out of the scope of what we're doing. Maybe I can show you some videos. I can actually, with this kind of problem, you can actually make this point, this point where you are stuck, asymptotically stable. Which means no matter where you start, you're going to converge here, which is obviously not optimal. Not, I mean, it's optimal with respect to what you find, but it's not optimal with respect to what you would like. Yes, that's a good one. All right, I think we are done. I don't want to start showing the simulation this time. So tomorrow, I think we are going to see how to implement that with this simple system. That's what we put to you. Maybe I can write a short simulation where you can see how the delta changes, how the P and the H change in all this situation. And we can look at this smart synthetic problem when you actually get stuck in this in simulation. Okay. With that, I think I'll see you tomorrow, as I said, in Auditorio 1030. Okay. All right, have a good rest of the day.